Welcome everyone. Thank you for joining us for today's webinar. My name is Véronica Royot from ICSAS20 Consultants in France. Today we are presenting using rigid blocks in PFC, presented by Sasha Emam. Just a little housekeeping before we get started. If you have any questions during the presentation, please type them into the question box in your GoToWebinar control panel. I'll bring them up during the presentation, and we will also have time for questions at the end. Now, without further ado, we will turn the time over to Sasha. Our presenter today is Sasha Emam, the PFC product manager. He is also one of the primary PFC developers and has been developing PFC models in ICSAS20 for more than 10 years. Sasha, can you hear me?
Yes.
Okay.
Perfect. Okay, so thank you very much, Veronique, and hello to everybody, and thank you for attending this short webinar regarding using convex rigid blocks in PFC. So we have like 15 minutes to go. I will give a brief overview of the rigid blocks logic as implemented in PFC 6, version 6. And then I will cover a few examples to demonstrate the utilities we added to generate rigid blocks and also to install stress in rigid block systems. So first, since the release of PFC 6, we have the ability to model convex polygons in 2D or polyhedra in 3D. The full inertia tensor of the shapes are used for the rotations, similar to what was done what is done with the clump logic in PFC. And those rigid blocks, they can interact between each other or with other model components, just like balls, walls. And they can use all the contact models that are available in PFC, so including the contact models that have a concept of bonding to create what we call bonded block models. The contact detection and resolution scheme uses a variation of the well-known JGK algorithm. And this implication of the way we implemented the contact resolution is that we have only one contact between an Rblock and another object. It can be a face-face contact or with a vertex for rigid blocks, or it can be also a face ball contact, for instance. We have the ability also to use a concept of rounding, which I will detail a little more later on, that can be used to improve the simulation time. So just a few old examples. So here, I don't know if you see my mouse pointer, but so on the left top corner, we have some rigid blocks falling down a slope. The left bottom corner has an example of cylindric rigid blocks that are rotated in a drum. And on the right-hand side, you have bonded models of specimens, so either like lab scale specimen. So the first one on the left has balls, but the two other ones have Voronoi rigid blocks that have a Voronoi that are that came from a Voronoi tessellation of the cylinder, and on the right-hand side you have a tetrahedra that have been generated as a tessellation of this space. And here it's another example of a parallelepipedic box meshed using a tetrahedra and then cut with the shape of an excavation. So I will detail those steps a little further later on. So to do those shapes, we have a few utilities that are provided in PFC. So first, you can create simple shapes like spheres, circles, boxes, so parallelepipedic boxes, cylinders, or cones in 3D. You have also the ability to import those blocks from a geometry set or from CAD data, if you have CAD data. You can supply vertices automatically to compute rigid blocks shapes. So if you issue a set of nodes, then you will compute a convex envelope for those nodes and create a rigid block. We have the ability to use templates if you are familiar with the clump logic and the clump templates in PFC. So we have exactly the same capability with rigid blocks. So you can create templates and then use those templates to create as many blocks as you want in your system. We have also the ability to cut rigid blocks with planar features or with a set of fractures, which are small either disks or triangles in 3D or small line segments in 2D. And this ability to cut the rigid blocks also provides a few capabilities in the way you handle slivers. So slivers are rigid blocks that have a shape that are either very elongated or very small. So when you do those cuts, to prevent from creating those hill-shaped blocks, you can decide to delete them or not cut the blocks, or you have several options. With those meshing tools, tessellation tools that I mentioned previously, so you have the ability to pack and create packings of blocks from tessellations. And you can also, and I will show that also, install stress states at contacts between the rigid blocks from a given stress tensor using a command. Okay, so I will just bring a few examples to demonstrate some features. So here is the first example, very simple, where we exercise the rigid block RBlock create command. So if I execute those lines here, you see we created a box at given locations in our system. You can also create circles, for example. So I can execute those lines. And here we created circles with different resolutions. So with a high resolution and otherwise with coarse resolutions here, for instance, or even on the left-hand side here. You have also the possibility, just execute everything here. You have also the possibility, as I mentioned previously, to directly specify some vertices, and then this would create a rigid block with this shape here by taking the convex hull of whatever the position I gave previously. So very soon, as we usually deal with a very large number of blocks, for sure we don't want to create them one by one in the system. So then what you can do is, instead of creating directly a rigid block, you can create a rigid block template with the same very similar commands. And here what we did is we created a template, and then this template, we could use it to fill a volume, for instance, using a RBlock generate or RBlock distribute command. So this is exactly what I do here. So here in this example, we create first a template, and then we tell PFC to generate 100 blocks using, so since we have only one template, you will use this template. We could have multiple templates and you would have used all the templates, or you can also decide which templates you can use and which volume fraction of which templates you want to use. So here, if I execute this file, so it created, it goes fast. So it generated 100 rigid blocks, as I told him, with a given size distribution. So here I specify that as a metric for the size of the rigid block, I want to use the diameter of the equivalent volume sphere. So here, those blocks have a volume of the equivalent sphere of diameter 0.05 to 0.1 with a uniform random distribution. And then, so once we generated those blocks, we have to specify attributes for those blocks. So the minimum set of attributes is the density to get a mass. And then we can cycle this model to equilibrium. Okay, and to go a little further, so here what I did is implement a function that just generates a random shape using the geometry logic, and then creates a rigid block template from this geometry object. So we create nodes, geometry nodes, and from those nodes, we will compute the convex hull of this set, and then create a template with different parameters. So if I execute this snippet of code, you can see that I generated different shapes, random shapes. So starting close to a circle and then more elongated. So here I have 5 templates. And then if I execute the final part of the code here, let me zoom in a little. We just, similar to previously, we just ask PFC to generate 100 rigid blocks from those templates. So we'll pick randomly each set of templates with some size distribution, activate gravity, and cycle. And this is the kind of system that I have in the end, with all my templates used to fill the space, and then this is settling under gravity. Okay, so this is the first kind of tools that you can use to generate clumps, to generate rigid blocks, or to create rigid blocks templates that you can use to generate rigid blocks afterwards in the simulation. Okay, you have also the ability to construct rigid blocks from tessellation of space. So for example, here, in this example, we asked PFC to generate a box using the geometry logic, and we use the RBlock construct command to, so from this box, create this tessellation here using triangles in 2D. You have also the possibility, once you have a geometry set, you have also some control on the mesh that is produced. For instance, here I can generate the same box. I refine it a little in order to have more nodes inside the geometry. And then you can assign a double value to the extra one of those geometry nodes that will inform PFC about the approximate size of the elements you want in this region of space close to this geometry node. So here in this case, what is done is, so for all the nodes that have a positive y value, so the top part of this model, we gave a size, some distribution size that we wanted with some randomness in this part of the model. And we gave a larger size in this other part of the model here. And now we can again use the RBlock construct command to actually create triangles that have no this information about the size ratio that you want in this model. Okay, so this is a basic usage of the RBlock construct command. And as you see, as we can provide information about somehow node positions, centroid positions, and values of sizes inside the material, we can inform to get an appropriate mesh. Another way to do that would be to use balls as the primary geometric information. And for instance, in this case, I use balls to create a Voronoi tessellation of space in this example. So let me bring the example, maybe it will be better. So in this example, what we do is we already packed some balls. So here I have a set of balls. I hope it's large enough for you to see everything. And from those ball positions and radii, we ask PFC to construct a Voronoi tessellation of this system. Okay, so here you can see for each ball, it created a Voronoi cell that maps the space. And you can see we have some boundary effects here on the side with larger Voronoi cells. But you have a one-to-one mapping between the balls and the rigid blocks in the system. Okay, so this is another way to create a mesh by first generating a pack of balls and then using this information to inform PFC how to generate a mesh. Then in this case, what we can do is delete the balls that have been used to generate the tessellation. Okay, then we also again set density. We tell PFC which contact model we want to use. Okay, and in this case, what we're doing, we're also creating an excavation in the middle of the system. So here we use geometry objects. We generate a circle, and we turn this geometric object into a set of fractures in PFC. So if I execute everything up to there, let me start from scratch here. So here we have our rigid blocks. And let me bring in my fractures. Okay, and I don't know if you can see very well, but here we have a circle, a set of line segments in 2D that we want to use to cut this system here. Okay, so you have the ability to do that. You can cut blocks with fractures. So if I execute this command, here is what has been generated. Okay, and you can see that here what I decided to do. So here in this case, we can see. So here this block has not been cut because it would have created very weird hill-shaped blocks. So some of the blocks here have been retained, so they are not cut. So you have the ability to play with those parameters. So here I told PFC to keep the slivers intact. So do not cut the blocks if it would have created a sliver object. Now if I continue here, so here we fix the position, the velocity of the rigid blocks on the boundaries, and we create the contacts. I already cut it. Okay, and the other important command I wanted to mention today is this RBlock traction command, which can be used to set up a stress state inside the material. So here it's in 2D, it's the XX component, YY components, and the XY component. So here, if I issue this command, PFC will have the ability to go into all the contacts between the blocks and install a force, a normal force that is consistent with this in situ stress state that I specified. Okay, here what we do is we bond all the contacts with infinite strength to remain in an elastic mode, and then we can delete the rigid blocks that are inside the hole, the excavation region, and we can solve this system. So if I just do everything back, so here I could put the displacements, for instance. So now here is the displacement field in my system due to the removal of this excavation here. Okay, so one note, and I'm not sure if we can see it. So one command that is important here is this rigid block traction command that allows you to install a stress state, that install contact forces from a stress state. And there is also this concept that I mentioned previously of rounding. So you will see either rounding or dilation or erosion in PFC. So it's the same concept with a few differences. The idea is that when you create your rigid block, you can use this rounding to limit the number of vertex contacts or contacts at the between vertices of your rigid blocks. So using this rounding, you have the ability to cull down the number of inactive contacts in your system, and then have a much more efficient simulations. Okay, and I had another example. So this is using this Voronoi meshing. Okay, But again, so an example that I didn't mention previously. Just to mention that, so the rigid blocks are also compatible with the periodic space logic in PFC. And so here, oops. So here we're packing again random shapes of particles within a system, and they have periodic boundary conditions. So you could also use periodic boundary conditions to install stresses, distort the periodic domain to install stresses in your material, and go from there. Where is my? I had the last example. Oops. Okay, never mind. Okay, never mind. So here we just use the same logic. We created grains using this small function, and then use the distribute command here to say, okay, I want to use those templates that are generated, and I want to distribute as many rigid blocks as I want to reach a target porosity. And then we can assemble this small brick into a larger specimen. And here, for instance, so what we have done, so we can install the stresses that we want, gravitational stress that we want. And here in this example, for instance, we just make a cone penetrate in this specimen, and here we color the blocks by displacement. Okay. So time goes too fast. So again, as for rounding, so I took this slide from another presentation. So here we have 3D examples where we meshed using a tetrahedra, a lab scale type of specimen of cylinder. Okay, and what you can see is that you may have this situation with many vertex to vertex contacts, which create many inactive contacts here in this case. So those inactive contacts, they don't affect the mechanical response of the model, but they affect the computational time. So you have the ability to use rounding to decrease the number of those inactive contacts and have a much better performances in PFC. Okay, so those are the main features of everything you can do with rigid blocks in PFC as of now. And I just wanted also to mention two upcoming features, which will be in the next version of PFC, which will be the ability to clump convex rigid blocks, to create concave shapes by clumping convex rigid blocks. And actually, this is a generalization of the clump logic. So you will also have the ability, I don't know for which kind of application, but to clump balls with rigid blocks, for instance. So you will be able to generate those clumps and then to release all the constituent rigid blocks as you want during the simulation. And I had already mentioned this ability to cut rigid blocks that we have. one improvement that will be added in version 7 is the ability to actually, when we cut a rigid block, we actually replace one rigid block by at least 2 other rigid blocks. And by doing that, at the moment, we lose the contacts information at the outer boundary of the blocks that we're cutting. So because we're deleting this block and creating a new block, we lose the contacts that were there. So if you are an advanced PFC or fish user, you can store those forces and then try to reinstate the contacts and the forces with the new geometry, with the new blocks that have been cut. But all of this will be available through commands directly in PFC version 7. Okay, so 15 minutes is a very short time. I hope I covered all the information I wanted to cover. I hope it was clear enough. Do you have any questions now or anything you want to discuss or want more information about? Please feel free.
Thank you, Sasha. Thank you. Yes, we have many questions. So I just want to select one or two. We have people who wanted to know if they will have access to the code of the examples.
Yes, and to the presentation too. Yeah, so everybody that's participated in this webinar, I guess, will receive an email, and we will provide information with those examples and the presentation itself.
Okay, and just one question from Reza from the University of Melbourne. He would like to know if you can just compare the computational demand of rigid blocks versus clumps assembly. Is it possible?
So I had something. Let me look. I have this information in another presentation, so let me quickly look if I can dig it in. Sorry, I don't find it right here. But so the idea is that the more facets you have with rigid blocks, the more computationally intensive will be the contact resolution. So if you have rigid blocks with many facets, this will slow down your code. The same way as with PFC, with clumps, so if you had many pebbles, you would increase the number of contacts and increase the computational time. So I don't have, I'm sorry, Reza, I'll come back to you with this information soon. So basically, what we find is that to approximate a shape using clumps, you need many pebbles if you want to approximate the volume reasonably. And so using rigid blocks in this case would be faster than using rigid blocks with fewer number of facets, smaller number of facets, will be faster than using clumps with many pebbles. Otherwise, it's approximately, if you have approximately the same number of pebbles as you have a number of facets to describe your rigid block, the time is so it's more computationally intensive than if you had balls, but the time between clumps and rigid blocks with the same number of facets or pebbles is comparable.
Okay, thank you, Sasha. As we have a lot of questions, I think you will give a reply offline. So I want to thank you. Is there anything you wanted to cover before wrap up?
No, thank you very much for attending. And yeah, so don't hesitate. I think I didn't give my, but so don't hesitate to contact us if you want more information or discuss. So as Veronique said, we will cover your questions that have been written. And if you have other questions, please don't hesitate to send us an email, and then we'll.
Yes, you can join us at software@itasca.fr, but I will give you more information offline. So thank you, everyone. We appreciate you being here. Thanks again for joining us today, and we will see you next time. Thank you. Thank you, Sasha.
Thank you, Veronique.
Bye-bye.
Thank you, everybody. Bye.